Guys, welcome back to part 2 of transformations of logarithmic functions. So we're going to look at this graph here. We're going to do it slightly different than we did the previous graph, where we pick some extra points and try to find the a, b, h, or k value. You're going to see later on that the b and the k value are essentially tied together. Like if I know one, I can do the other. They're interchangeable. If you find one, you can find the other. The a and the b, they're kind of separate from each other. And the h and the a's are somewhat connected, but not really. You'll see that later on when we talk about log laws and how they could be connected to each other. So to analyze a graph like this, if I'm going to do it by key points, you can see up here, I'll just scroll a bit. They give you a little hint here, use key points to determine one of the transformations, if it's horizontal or vertical kind of stretching. So I'm going to look at this graph here. We already determined before that this second graph here, the green graph, is your original graph, right? And then this black graph is one we're trying to transform to. So we have some good key points on this graph here. You can see some nice intersection points here, such as 2, 1, 4, 2, and what's this one? 8, 3. All right, so looking at those points and then looking at points that correspond to those ones, and I'm looking at the ones that go kind of horizontal. If I look at these ones here, you can see it. I'm going to give you two answers here. If I go straight up, you notice that this is a nice point 2 units up. I go straight up. This is a nice point 2 units straight up. This is a nice point 2 units up. And you notice that that's common. So there's an upwards translation of 2 units. Because of that, I probably say that my k value is 2. And that's all I really need. So I just analyze the graph and I determine that g of x is just log base 2 of x plus the 2 units that shifted the graph up to that k value. But I could also write this as something else too. So let's look at the horizontal translations. Let's use green. So if I take this point and I go over to this point over here, this is a nice point, and I read this one as 1, 2. Or if I take this point and read it all the way over to this point, which is 2, 4, or 2, 3, sorry. I'm sure I can find some other points, maybe this point here. You can't really read this one too well. But maybe we can kind of guess what that point is and say that's a half and 1. All right. So if I look at all those, and you look at just the, you see the y values are staying the same. So I'm not doing anything up and down. But if I look at the side-to-side part, like x values, I can see one from 4 to 2. Okay, maybe that's just shift 6 over, but that doesn't match the other one. So they're not all 6 over. To the left there, so maybe it's like a divide by 4. So I could take 8 divided by 4, 4 divided by 4, and 2 divided by 4. Yeah, 8 divided by 4 is 2, 4 divided by 4 is 1, and 2 divided by 4 is a half. Okay, so that means my b value, or my stretch factor is a divide by 4. So I could say that this is a divide by 4. Oh, 4, put a 4 there. And because of that, my b value is 4. Remember, it's a reciprocal. So I'm dividing by 4. The factor that I have is a quarter. Okay? If it's a quarter, then my b value is going to be 4. So I can write this now as g of x log base 2 of 4x. And so these two graphs will essentially give us the same thing. Later on, you'll see that these two graphs are exactly the same thing, this plus 2 on the outside or this 4x on the inside here. And they can be written in different forms using different laws that we have. So both of these graphs are essentially the same. Okay, so that's how that works. We're going to do a little word problem here. The reason I just throw in a word problem is because you can see some word problems and some tests that we do. So let's just read through this one and see what it says. You have this equation here that says the frequency of a musical note can be determined by this equation here, where n, or 12, n is equal to, where n is the number of notes away from, away from the note A, and is equal to 12 times log base 2 of f over 440, where f is the frequency of the current note that we're looking at. It's also measured in hertz. That might be useful for later on. So they just want to know how many notes away from A. So they're looking for n in this situation. What is n? That's how many notes are away from A. If I'm given a frequency of 82.407 hertz. All right, that seems pretty easy. You just plug it into our equation that we have there that they gave us. So 82.0407 divided by 440. And we're getting the equation. So if I punch this on my calculator, I'm getting approximately minus 29 notes. Now I get the negative, so that's key. That means it's probably below A. So I can probably write this down and say 29 notes below A. Okay. The reason I say below, because look at this next question. It says here, what's the frequency of that one that's above A? 6 notes above A. So I could say that in this question, that they want to say the N is 6. What's the frequency of that one? Now, we'll do this, and we'll look at this equation. I'm going to put in what we know, just like the one we just above it. And then we're going to try to isolate for our unknown variable here, so the F variable. But you notice the F is inside the log, so we're going to use our log laws that we had before. So before I could do the log law, or the log identity, or whatever you want to call it, the switch between exponential and logs, I'm going to divide over the 12 first because I need to get the log by itself. So I can apply the exponential form. So 6 divided by 12 is a half. And now I can change this into exponential form. So remember how that works is that you switch these two things. So whatever's inside the log pops out of the log. We'll deal with the divide by 440 later. We got a base of 2, so these two things are the same. And then this other guy becomes the new exponent. So that's just the square root of 2. All right. I'm going to rearrange this equation. Let's just put it over here. So I'm going to times up the 440, because right now we would divide by 440 on the left side. And then I'm going to times that with 2 root a half. So I'm not going to put these together. I'm going to go say that's 880. That's not allowed because the exponents are not the same. If the exponents were the same, yeah, go ahead and combine them together to make your life a little bit easier. But then we just punch this into our calculator. I'm just looking around for my calculator. Go back over here. Well, it looks like I left my calculator at home. So let's just punch up another calculator here while we wait. Let's talk about our day and see what we have here. I can make a guess here. It's probably in the 600s or something. This is about 1.414 times 440. So about 50% of this here is 220. So I'm gonna say it's in the 640s ish. Yeah. So I'm just gonna pause the video while I wait for this to go. All right, so back at it. So we've got a calculator open. So 440 times 2 to the power of a half. I was going to 0.5 for that. Oh, 620. Okay, so a little bit off. 622. 622, approximately 622 hertz. And there we go. All right. So the next video, what we're going to do for the next video is we're going to talk about what these log laws I was mentioning before, and what are they? How do they work? And we'll see if we can apply them to solve some questions, make our lives a little bit easier. And I'll see you next video. Bye.